So welcome. So last time we were talking about capacitance, and we saw that it wasn't a really good energy storage device, but it tends to be useful in terms of things like tuning circuits and filtering systems for electrical circuits. That's where most capacitors tend to be used, although it can be used as a storage device. If you have one of those zappers, it's probably got a whole bunch of capacitors inside it. So let's talk a little bit about the energy stored inside a capacitor. So what we do, I need to go down and get my pen. So what we do is we basically say, consider charging up a capacitor. As the charge increases, the potential difference between the plates increases. It's literally like taking a spring and compressing it. As you compress it, the thing resists you more and more. As you put more electrostatic charge on those plates, adding more is harder and harder to do. So important thing to realize is the first electron is easy to put on an empty capacitor, but the last electron is really hard to put on. And eventually you get to the stage where you don't have enough energy to get the next electron on, and you are fully charged. So it's like you just put a whole bunch of springs inside a tin box, and if you open those springs, just open that box and flip them out, you're going to get all that energy back. So it's a nice, when there's no friction and when there's no resistance, you get what you put in is what you get out. So it's kind of like potentially really nice, actually, but you just can't store that much. Consider an instant when the charge on the capacitor is positive Q. The associated potential difference, well, you know, we learned capacitance equals the amount of charge over delta V, so swap those two guys over. So this is your charge, and this is your capacitance. The work required to transfer a little bit of charge dq of the charges across the capacitor, well, a little bit of work is equal to my voltage. Let's think about units for a minute. Voltage is joules per coulomb times my little bit of coulomb. That's going to be joules, which is work. So from a units point of view, that makes sense. And we just realized that delta V equals Q over C, so there's my Q over C. I've got to multiply this by a little bit of Q. So what I say is the total work required to charge up a capacitor from 0 to big Q is the area under a voltage versus charge graph. So I'm adding more and more charge, and I'm getting more and more voltage. And so here I've got to stop for a second and just point out to you the fact that I can talk about voltage in terms of the EMF that I apply to the plates. I apply 6 volts, current flows, adds more and more charge, and at the end I will find that I have a potential difference of 6 volts across the plates. Now I'm using voltage in 2 ways there. I'm using it in terms of an EMF. That's the driving force of my power supply. And I'm using it in terms of a voltage drop. That is what's dropped across the component. Okay, so you can talk in terms of voltage in terms of 2 different ways. And when you say C equals Q over V, if you say, well, I want to know, I have a capacitor and it's fully charged, and this is how much charge is on it when it's fully charged, and this is the amount of EMF I provided, that equation works. So by saying C equals Q over V, I could mean the total charge over the applied EMF, and that works. That equation works. But I can also talk about this circuit by not looking at the power supply, just looking at the, so I'm going to draw down here if you can see it. I'm sorry, this is like, it's always tough on this to find a place. So I'm going to draw it here. So basically I could have my power supply and I could have my capacitor, and I can be talking about the EMF of the power supply and the charge on the capacitor. And when I'm fully charged, then my capacitance is equal to the total amount of charge over the EMF that caused it. Yeah? But I could also take a voltmeter and just look at the voltage drop across the capacitor at different times. And what I'd find is that any instant the charge on my capacitor equals my capacitance times my potential difference. In the end, my potential difference will equal my EMF, and my charge will equal my total charge, my fully charged charge. But this equation also works instant by instant. So sometimes I'm talking about the voltage as being the EMF that I'm applying and the final result of charge. And other times I'm talking about this voltage as being the potential difference across the device and the instantaneous charge that's on the device. Okay, so that equation can be used in two different approaches. So watch out for that. So here I'm talking about not the EMF that's applied, but the actual voltage potential difference. So this is my potential difference. If you like, as time passes, as my potential difference increases, as time passes, then I am getting more and more charge on my capacitor. Why? Well, the charge is creating the potential difference. So it's kind of like the EMF causes the charge to flow, but the charge residing causes the potential difference. And so we get this. And it kind of leads to a little bit of confusion when you first begin, because you say, I thought voltage was EMF. Well, it is some of the time, but other times it's the potential difference. So, okay, so I got a graph and realized that when you have a little bit of charge on there, you have a little bit of potential difference. And when you have a big piece of charge, a lot of charge in there, you have a lot of potential difference. So this is a nice linear graph, and it's not level, it's sloping. So we say, well, let's have a look. The total work done to charge up the capacitor from 0 to big Q is the area under this graph where this is 0 and this is big Q. So the common mistake is, because you're given big delta V and you're given big Q, is to multiply those two guys together. If you did, you'd be taking that square, which is clearly not what's going on. We've got to recognize, oh, as this Q increases, my voltage increases, so it's a triangle. So let's have a look. This would be, fancy terms, we'd say it's the integral of little q over c times dq. So I'm integrating that with respect to dq, so I get 1 over c is a constant, q dq, which gives me 1/2 q squared over c. Okay. Now, graphically, what jumps out at me is, oh, this is 1/2 q times delta v. That's what the area is. So graphically, I get this. Using integration, I get that. So how do they relate? The energy is equal to 1/2 q squared over c, which equals 1/2 q delta v, which equals 1/2 c delta v squared. So the way I approach this is, I know really well that, because it comes from the graph. And I also know that c is equal to q over delta v. So if I want, I can substitute in for q and get 1/2 c delta v squared if I substitute for q. And if I substitute for v, I get 1/2, let's rearrange this, q squared over c. Did I do that right? Yeah. So I know that one. I know that one. I can get the other two. So I'm not going to learn 4 equations. I'm going to figure out the other two. If need be, you've got to learn 4 equations. Okay. Let's look at this. If I double the amount of charge on my capacitor, I 4 times the energy. That's interesting. Well, for a given capacitance, and so on. There's a little thing here which is, and it's going to come up a few times. I sometimes ask you to plot a graph of, something versus something. And sometimes, depending upon, you got 3, in this case, 3 equivalent equations, and you look at Q, and energy has got a Q squared relationship there. And it's got a linear relationship with Q there. And it's like, what's going on? And it's because delta V is not fundamental. It's complicated. And so it's hiding a Q inside it. So to find out what the true relationship is, you've got to go down to something really fundamental like capacitance. The capacitance is the capacitance. It's bomb. It's a physical thing. You can't change it. For a given capacity, you can't change it. So this comes out occasionally. So as a teacher, I got to be careful that I'm not thinking about one form of the relationship, but there's another equivalently good form of the relationship, and I'm especially got to make sure I'm not thinking about the one that's not the fundamental one. So I got to watch out for that, and you've also got to watch out for that. That sometimes there's more than one form of a relationship. How much energy is stored in a 6 farad capacitor? So here's my 6 farad capacitor. You put little terminals on the end so it looks nice. 6 farad capacitor. If it holds 5 coulombs of charge, so this is, let's put our charges on here. I suppose I could put down 5 little positives and 5 little negatives, but it doesn't really mean 5 coulombs. But okay, so we have that. Notice I'm not even concerned about an external EMF. Maybe I probably had one. I must have had one to drive the charge onto there. It's disconnected, or I'm just not concerned about it. All I need to know is the capacitance, the charge and the capacitance. That's all I need to know. So C is equal to 6F, Q is equal to 5C. Why am I doing my list? Because I don't want to make the mistake of C being charged and looking across here and thinking that it's a capacitance. I want to be careful on this. And I know that my basic definition, the capacitance equals the amount of charge you got on your capacitor over the potential difference across it. And let's have a look. What do I want to find out? How much energy? So my energy equals, my U equals, it really should be, that's the equation that I used. Okay, so I know from my graph that U is equal to 1/2 Q delta V. Let's have a look. I don't have Q and delta V, so I take these guys and I say, well, U is equal to 1/2. Let's substitute in for Q, and I'm going to say C delta V squared. Let's just double check on that. Q is equal to C delta V. Q is equal to C delta V. And I have a C, and I have a Q, don't I? So then I want to go the other way and say U is equal to 1/2. Get rid of the delta V, so that's going to be Q squared over C. Let's double check on that. I take my delta V equals Q over C, that's Q squared over C. Yes. So this is going to equal 1/2. And my Q is 5, and I've got to square that over my, my C is 6. So that's going to be 25 over 12. Whatever that works out to be. So U is equal to 2 point something. Did I do that right? 2.1? Sorry? 2.1? 2.1. What the unit's going to be? Joules, yeah. We worked in SI units, so we don't need to worry about what else. It's in joules. So how much energy is stored in a 9 farad capacitor when it's fully charged by a 9-volt battery? So now we are talking about the battery. So here's the 9-volt battery. Here's my capacitor, a 9-volt battery, and this is going to be a 9 farads capacitor. So my delta V is equal to 9 volts. And my C is equal to 9 farads. And I want to find my energy. Energy equals, I don't know. And I say, well, let's look. U is equal to 1/2 Q delta V, because I know that really well. But I want to get in terms of my C. So let's rearrange this a bit. U is equal to, if I substitute in for the Q, I get 1/2 C delta V squared. How do I know that? Because C is equal to Q over delta V. So let's look. I got C, and I got, oh, that'll do it. So then I simply say, okay, well, U is equal to 1/2. My C is 9, And my delta V is 9 squared. So that's going to be 81 times 4.5. And that's 32, 320 and a half of 81. Might as well do it in my calculator. Why did I do that? 364.5. 364.5. I was told that if I do more mental math, then I'll stay mentally younger, which means that I'll be more alert as the rest of my body just falls apart. You know, it's like, it's a mixed blessing, but, you know, I'm going for it. So, okay. So not bad, yeah? It's like a couple of equations with a little bit of math, and you can get it. Most common mistake, people think C is capacitance when it's 5 coulombs. They get the units mixed up with the parameter. So as I think I've told you before, sometimes, I mean, people sometimes will do a different kind of C for capacitance than they'll do for coulombs. And it's probably really worth it, you know. Okay, so that's how much energy is stored on a capacitor. Then how is the energy stored in the capacitor? And it's basically stored in terms of the electric field. So we say energy is stored in the capacitor, you know, delta V equals minus ED. Let's just check our units again. So this is newtons per, let's have a look, electric field, newtons per coulomb, N over newtons per coulomb, and then we're going to multiply it by distance, delta x. So that's going to be, goes from force per coulomb to work per coulomb, and that is what delta V is. So that kind of makes sense. And then we know for a plain plate capacitor that C is equal to epsilon naught A D. We're assuming here that K, my dielectric constant, equals 1. So it could be air-filled or vacuum-filled. And we say, well, let's play the game. So U is equal to half C delta V squared. Let's substitute in for C, a half E naught A, epsilon naught A over little d. And my delta V is equal to minus ED, but I've got to square it. So that's a half epsilon naught A D E squared. So U is equal to a half epsilon naught A D times E squared. I've got to be careful to not think that that's DE, but that is D, a little a separation, times E squared. And so what I say is that my energy per unit volume, why do I want to know that? Because at some point, I mean, engineers want to know, well, how much energy could I store in this room? You know, because volume is real estate, and volume is expensive. So how big a capacitor bank would I need to store this energy? So I have my energy over my volume. My volume, of course, is equal to A times D. It's actually the area times the separation. It's that plate area times that separation, which is V. So, okay, that's interesting. So that means a half epsilon naught times E squared, which is kind of interesting. The energy per volume is equal to a constant times the electric field squared. So if I can make the electric field bigger, then I will get more energy storage. And I can make my electric field bigger by making the potential difference across it greater. That's one way of getting more. I mean, that makes sense. You put more potential difference across the capacitor until it breaks down. Eventually it's going to break down, but until it breaks down, you're going to get more energy stored in it. This expression is valid for many different capacitor configurations. The energy density in any electric field is proportional to the square of the magnitude of electric field at a given point. Oops, and there we have it. Of those two, I clearly care about the amount of energy stored a bit more than the energy that could be stored in the electric field. But, you know, it's quite accessible. That second bit is quite accessible. So let's stop.